Welcome to Ancient Revelation, the #1 investigation network, decoding primordial secrets of the Earth.
It's perhaps the holy grail of planetary science.
Are we alone in the universe? It's one of the grandest questions we could answer.
We don't really have a definition of life, but I think I'll know it when I discover it.
Life can take many twists and turns, and I think the really cool thing about it is the variety that we're going to be able to find elsewhere.
Are we a lonely planet? Or does life exist beyond Earth? Members of the groundbreaking field of astrobiology have joined forces to solve this enduring mystery. Life. Is it rare in our universe? Or is space a galactic zoo, teeming with all sorts of creatures?
Everybody has this sort of iconic view of the aliens. They're going to be little gray guys with big eyeballs and small noses. Well, maybe, but I don't think so.
On far-off planets, life may be as far out as buggy-eyed microbes or sci-fi sea monsters like galactic manta rays. Others may be home to cybernetic organisms, hybrids of biology and machines.
One way to get a handle on thinking about super advanced aliens is to try to imagine the possibilities of our own future. Maybe it'll be machine-enabled humans. I feel like I've already become a machine-human hybrid. I mean, I have this laptop computer that I take with me everywhere, which is really kind of the third hemisphere of my brain. My body's even changing and becoming sort of shaped like a person using a laptop computer, and so I'm becoming Homo laptopicus. It's likely that the universe is full of life. We don't have evidence yet that we're not alone. So we're out there and we're looking.
When it comes to hunting for alien life, planetary scientist and musician David Grinspoon walks to a different beat.
I do wonder, in terms of extraterrestrial life, whether they'll have music or something like music. Music is fundamentally waves and rhythms, and that's sort of the nature of our universe. There is a certain musicality of just the fact that it's all vibrations and waves and rhythms and modulated tones. So I can imagine, and this is just my wild fantasy, some analogy to world music far in the future where we're mixing our musical cultures with alien musical cultures. I think you'll get many different shades of astrobiology if you talk to different scientists, but I think you'll get a lot of agreement on the broad goals. We want to find life elsewhere, but in the meantime, we're learning a lot about the history of life on Earth.
In the field of astrobiology, one of the fundamental goals in searching for life elsewhere is first figuring out how life evolved here on Earth.
One of the big unsolved mysteries in astrobiology, of course, is how life got started on Earth. Because if we could understand that, then we would have some insight into whether it could have gotten started elsewhere.
Earth orbits in what's called the habitable zone. It's a region of space where conditions are favorable for life forms that we know can be found on our planet. We are at just the right distance from the sun, so our oceans don't evaporate. Our temperatures are not too hot or too cold. And we have oxygen in our atmosphere, so we can breathe. Earth's been a cosmic paradise for all types of life, from small single-celled organisms such as bacteria to large multicellular mammals, including man. It's believed that all life on our planet descended from a single common microbial ancestry, approximately 3.4 to 3.8 billion years ago. But how that microbe came into being remains puzzling. One way to search for answers is to look for ancient rocks, where microbes leave trace evidence of their existence.
Geology is a crucial tool for understanding the origins and evolution of life on Earth, because the historical record of life on Earth is almost entirely recorded in the rocks that we walk on.
Geologist Abigail Allwood's journey to discover the origins of life took her no farther than her own backyard. The Pilbara region of West Australia contains some of the oldest rocks on our planet. They're almost 3.5 billion years old.
The Pilbara contains rocks from the early Archean era that have survived on the Earth today. They contain several rock units that contain possible evidence for life.
Planet Earth has been around for over 4.6 billion years. But most of its original surface has been obliterated by plate tectonics and erosion. The extremely thick crust in the Pilbara has helped it resist destructive geologic processes.
The Pilbara hasn't been strongly affected by plate tectonics, and the original features in the sedimentary rocks are more or less ready for us to interpret. There are also sedimentary rocks of similar age, almost 3.5 billion years old, in South Africa. So far, the Pilbara seems to have yielded a richer fossil record.
Allwood spent more than 3 years surveying some of the rock formations in the Pilbara, examining unusual structures called stromatolites, fossils formed by living organisms 3.5 billion years ago.
They realised that what we were looking at was the remnants of an ancient reef, a microbial reef. It's not a reef made of coral like we're familiar with today, but a reef made of stromatolites, structures formed by microorganisms.
Stromatolites are rocky structures that form on the sea floor, where fine layers of sediment are built up into cones, domes, and other shapes over a long time with the help of tiny organisms. A stromatolite is not alive, but is a structure made by living things. When we find one in the fossil record, it is like finding the footprint of long-dead microorganisms. But the microbes themselves are almost never preserved as fossils inside the stromatolites. And without that, it is extremely difficult to be sure an ancient stromatolite is proof of life. But in this case, Allwood found that the Pilbara stromatolites are in fact biological. She just may have discovered the oldest evidence of life on our planet.
These stromatolites are the oldest convincing evidence of life on Earth. And these amazing pronounced conical structures that are not like any kind of wave ripple or a structure that you'd expect to see on the seafloor where there's no biology. These are interpreted as stromatolites, sedimentary structures formed by microorganisms that lived at the interface between the sediment and the ocean.
Allwood used geological techniques to interpret the environment these fossilized microorganisms may have lived in almost 3.5 billion years ago.
What we saw was that immediately before the stromatolites formed was a setting pretty much just like this, a rocky coastline. We see that the stromatolites only exist in the shallow water environment and don't exist in the deep water areas that were existing at the same time.
This fossilized ecosystem provides a glimpse into the past and what might be the remains of man's earliest ancestors.
With the rise of astrobiology and new techniques and approaches to interpret evidence for life, we can be fairly confident about saying that life was on Earth at least 3,430 million years ago.
But could life have existed even earlier on our planet?
The oldest evidence of life is not evidence of the oldest life. We do not have any geologic record for the first 500 million years of Earth's history, so there's a whole bunch of stuff missing.
What's not preserved in the fossil record is how life formed in the first place. We humans are the descendants of stardust. 4.6 billion years ago, stellar debris created vast clouds of gas within our solar system. These gaseous clouds formed dust particles, which stuck together. They eventually formed large boulders made of rock and ice called asteroids and comets. For millions of years, these bodies collided and coalesced to form planets, including Earth. During this heavy bombardment, Earth was a hot, toxic water world. But in the midst of this volatile period, life may have taken hold below the ocean surface, in hydrothermal vents, which are formed near volcanoes. There, atmospheric chemicals and energy may have formed a cocktail of amino acids, the essential elements of life.
One of the popular hypotheses is that life arose around a hydrothermal vent because of the particular conditions there, that it would have been a deeper water environment which offers protection from impacts. Shallow water environments would have been very hostile during the period of heavy bombardment.
But the key question for astrobiology is, where did the spark occur that took non-living matter and turns it into living matter?
Chris McKay is a giant in the field of astrobiology. The NASA scientist has spent over 25 years trying to decode the origin of life on Earth and find it elsewhere.
There's a whole set of theories that suggest that everything needed for life started and was created here on Earth. So the organic material that led to the first life could have been produced in lightning discharges on Earth. An alternative theory is that the organics that led to life weren't created on Earth, but came into Earth. Comets, for example, could be a source of organics. Meteorites from Mars or asteroid infall could have been a source for organics. So now the raw materials are imported, but life is still homegrown. Yet another theory suggests that not only did the organics for life come in, but life itself might have come in from outer space. We don't really know how to choose between those three alternatives.
All life on Earth is made up of essential building blocks, including carbon, hydrogen, oxygen, and nitrogen, as well as 24 other ingredients. But the fundamental properties appear to be water and carbon.
The carbon in water model of biology is the one that we're familiar with, and it seems to be the best way for biology to operate.
Scientists think the best chance for finding extraterrestrial life is to search for traces of carbon and water on planets in our own solar system. Mercury and Venus are too close to our Sun to sustain liquid water or an Earth-like atmosphere. But what about Mars, the fourth planet from the Sun?
Studying the oldest evidence for life on Earth is relevant to the search for life on Mars. We have strong evidence that sometime in the past, Mars may have been more hospitable, wetter and warmer, had an atmosphere.
Today, Mars looks like a dusty red desert. Its atmosphere is so thin that liquid water would freeze and evaporate at the same time on its surface. But Mars's topography reveals polar ice caps, gullies, and volcanoes, including Olympus Mons, the largest in the solar system. So could liquid water still exist beneath the surface, where temperatures are warmer? believe the best chance for finding life beyond planet Earth might be next door in our solar system. Mars, the fourth rock from the Sun, may have liquid water beneath its surface, a good signature for life.
Hydrothermal systems can definitely exist on Mars though, because we can see massive volcanoes. We know there's plenty of water still on the surface of Mars. That heat source, the water source, provides all the ingredients necessary to make microbial life very happy.
To better understand the geology on Mars, astrobiologist Dr. Adrian Brown investigates the hotspots on Earth, particularly Lassen Volcanic National Park in Northern California.
The reason I'm interested in Lassen Volcanic Park is because of these hydrothermal hotspot areas where we can find minerals that are forming that don't form anywhere else but these areas. These sulfate-rich minerals that we see in the sides of the hills here are areas that we think that are analogous to Mars. And the fact that they're still active today means that we can get an idea of how friendly they are for life.
Hydrothermal hot springs are formed near volcanoes. Deep underground, the searing heat of volcanic magma chambers propels hot water and dissolved minerals into cracks and fissures in the subsurface, which then erupts onto the surface of the Earth. The spring surrounds itself with a treasure trove of energy-laden minerals suitable for a microbial feast.
A hydrothermal spring, just like the one behind me here, would be exactly the place that we want to land on Mars. This sort of area would be just perfect for life to exist, perhaps even for life to form, the origins of life. This area where water has been forced up through conduits and carried along minerals, energy sources to the surface and then spread them out around the deposit for microbes to feed on as an energy source.
Brown thinks if Mars is still volcanically active, similar hydrothermal areas will exist. They might be places where life may have originated or still exists just below the surface.
Mars is the red planet that we see from orbit, but just underneath a thin layer of dust, we see a whole rich array of sulfate-rich minerals that many scientists believe may have been formed hydrothermally. And we see those very similar minerals in the rocks and the hills surrounding us here at Lassen.
In 2006, NASA's Mars Reconnaissance Orbiter probe arrived at the red planet. It's equipped with the Compact Reconnaissance Imaging Spectrometer for Mars, better known as CRISM, which plans to revolutionize our view of the planet. Using visible and infrared light, the instrument has been scanning for evidence of ancient liquid water in Valles Marineris, a massive canyon system ripped into the surface by the volcano Olympus Mons. The area may hold hydrothermal deposits.
Mars is unlikely to be active at the moment, but in its active phase, it may have been that hydrothermal waters were driven by the massive volcanoes that we see on Mars today. And Mars may have been able to form active hydrothermal systems such as this and build up a rich layer of sulfate minerals on the surface of Mars.
Early Mars was much more habitable than the current day Mars. The planet cooled off. It's now too cold and too dry to support life. So if there was early life on Mars, it's probably not on the surface anymore, and it could potentially have migrated into the subsurface, into habitable environments below the ground.
Research scientist Jennifer Heldman is also on a quest to find life on Mars by understanding how microscopic organisms survive in extreme environments on Earth. But instead of investigating the hotspots on our planet, she scours for life in cold places.
Right now, specifically at Lassen Volcanic Park, we are looking at snowpack deposits. And we're especially interested in these snowpacks because they have snow algae living in them. So in the late spring, summer months, you'll see the snowpacks colored bright red, streaks and ribbons of red running through the snowpack. And that's the algae, so there's actually life living in these snowpacks. And so we're studying the physical conditions that the snow algae like to live in and applying that to snowpacks on Mars to see if the same conditions within snowpacks on Mars might exist.
NASA's Mars Global Surveyor has recently discovered Martian gullies that could be the ancient remains of snowpacks.
We're looking at these to study this phenomenon. Can those snowpacks actually melt, generate liquid water, and also potentially provide habitable environments for life?
To better understand snowpacks on Mars, Heldman conducts experiments in Lassen Volcanic Park.
So this is our setup for measuring temperature and light profiles through the snowpack. And what we're doing is using this instrumentation to understand the physical conditions within a snowpack that are able to support snow algae. This winter, this will get completely covered in snow and buried. And so we have sensors mounted on a pole here. So we have some moisture sensors here and here. And then these little ones are just temperature sensors. And then at the very top of the pole, we have a light sensor, which measures incoming solar radiation. And then down here, covered in the bucket, we have a tipping rain gauge. And this will measure the amount of liquid water that flows down through this bucket. The snow algae that we're seeing here thrives in these very low condition environments. It's very happy being at 0 degrees C. It's very happy in low light conditions. It's very happy in the nutrient poor conditions of a snowpack. Once we understand the conditions that support life here in the snowpack at Lassen, then we're also doing studies of snowpacks on Mars. And if we find the same conditions on Mars, you have to ask yourself the question, well, if these snowpacks on Earth are habitable, could those snowpacks on Mars also be habitable?
In addition to Martian gullies, two massive polar regions may also be places where life still exists on Mars. On August 4th, 2007, NASA launched the Phoenix Mars Lander spacecraft. When it finally arrives on the red planet in early June, it will probe its icy poles. Aboard the craft, robotic arms and dig trenches will plow through the layers of water ice to see if there are organic compounds, the building blocks of life.
We might go to the polar regions on Mars, drill down into the ancient ice, bring up organisms that are dead, they've been shelled by radiation, but we might be able to, by studying their biochemistry, patch them back up and resurrect them.
But even if Mars holds liquid water, could it have ever sustained larger animal life? When searching for Earth-like life in our solar system, scientists look for the presence of liquid water and carbon. They're crucial ingredients for life on Earth. But are there other indicators? Some scientists believe plate tectonics is necessary to promote biodiversity and act as a defense against mass extinctions. On Earth, plate shifting created continents. Without land masses, Earth would have remained a water world, and therefore, many species, including humans, may not have evolved. So why does plate tectonics exist on Earth and not on other terrestrial planets, such as Mars?
Because Mars is smaller than Earth, likely its interior cooled off faster. And it cooled off before really plate tectonics were able to start on Mars. Fortunately on Earth, we still have plate tectonics. And plate tectonics is the grand recycling system of our planet, recycling materials in the atmosphere, in the surface, and the subsurface. And Mars never had that.
Plate tectonics also keeps Earth's temperatures moderate by recycling chemicals to keep the volume of carbon dioxide in our atmosphere uniform.
Lacking plate tectonics, it didn't have the persistence of Earth. It developed maybe habitable conditions and maybe complex multicellular life very quickly, and then it dies off because it doesn't have the long-term potential that plate tectonics gives the Earth.
Plate tectonics may be one indicator for Earth-like life. But evidence suggests there may exist another type of life on a moon that belongs to the Lord of the Rings. In 2004, NASA's Cassini mission conducted flybys around the gas giant planet of Saturn. A year later, the spacecraft released its Huygens probe into the atmosphere of Saturn's largest moon, Titan. The images revealed that Titan has similar features to Earth, such as weather cycles and volcanism.
Saturn's moon, Titan, is a very complex place with rainfall, and rivers, and seasons, and meteorology, and a complex atmosphere, and interesting chemistry. Again, it's not going to be our kind of life, but there are flows of energy and organic compounds, and some other kind of life could flourish.
Radar imaging data has revealed the presence of liquid lakes on Titan. Although they're comprised of ethane and methane, they may be reminiscent of what water on Earth was like 4 billion years ago.
Titan, the moon of Saturn, is a really cool place, literally and figuratively. It's so cold that there's no liquid water. The ice there would be as hard as rocks, water ice, but there is a liquid methane, liquid ethane. So maybe there's life. Maybe life doesn't need liquid water. Maybe life can survive on another liquid methane.
Titan's temperature is a chilly -289 degrees Fahrenheit, but it has a nitrogen-rich atmosphere which produces hydrocarbons that can stay liquid at cooler temperatures. So it's possible that Titan may be hospitable to a new type of so-called extremophile, an organism that thrives in extreme environments. In the case of Titan, they may be psychrophiles, bacteria that thrives in frigid temperatures and uses methane to produce energy. Chris McKay has observed psychrophiles under ice-covered lakes in Antarctica. Some organisms live at the bottom of these waters, where their biological activities have created a zone devoid of oxygen and rich in organic molecules like methane.
One of the interesting ecosystems in the Antarctic are the ice-covered lakes, which have a persistent ice cover of about 15 feet of ice. Below that ice, there's liquid water. Given that there's water, it's not too surprising that there's algae and bacteria living in that water.
Like Antarctica, Titan's lakes may also contain similar extreme organisms that survive on methane. And Titan may not be the only moon harboring life. In 2003, NASA's Galileo space probe snapped pictures of Jupiter's moon, Europa. Evidence suggests liquid water may exist underneath its frozen crust. Scientists think Europa has an ocean that's over 50 miles deep. There are also signs of volcanic activity. So Europa's icy water could be warmed to a liquid state by volcanic vents on the ocean floor. And this volcanic activity would aid in cooking up chemicals necessary for life.
We have very convincing evidence that below the icy surface, there's an ocean. Ocean, water, maybe life. And we also have evidence that there are possible energy sources in Europa. So all the necessary ingredients for life seem to be there.
The ice on the surface of Europa is extremely thick, maybe as much as 6 miles deep. So it is unlikely that a human spacecraft will be able to drill down into its ocean anytime soon.
I think a realistic mission to Europa would be to search the surface for evidence of organisms that have been carried up through the cracks and deposited on the surface. They would be dead, but they would be biological and we could study them.
Our solar system is full of diverse, interesting places, and we shouldn't rule any of them out for life until we explore broadly, because we don't really know what we're looking for.
Armed with new technologies, astrobiologists have widened their search for extraterrestrial life. The next frontier includes our entire Milky Way galaxy and beyond. Astrobiology is pushing back the boundaries of modern science. Researchers now have the technological instruments to locate exoplanets. These are planets that exist outside our solar system. Exoplanets need to pass several tests in order to be considered suitable for Earth-like life. Most importantly, they need to be within a habitable zone of a central star like our Sun in order to support liquid water.
Our star is just right. It's not too hot and it's not too cold. And so we're just right in this perfect area where life was able to evolve.
In 2008, NASA plans to launch a space telescope called Kepler to search for terrestrial Earth-sized planets. The spacecraft's instruments will be able to detect exoplanets by measuring changes in a star's light curve as a planet passes between the star and the spacecraft. Jeff Marcy is one of the world's leading planet hunters.
We would estimate that there are some 50 billion, maybe 60 billion Earth-like planets within just our Milky Way galaxy alone. And remember, our Milky Way galaxy is just one of hundreds of billions of galaxies out there, more or less like our Milky Way. So the number of Earth-like planets in our universe is a nearly uncountable number.
But locating exoplanets is only half the battle for an astrobiologist. In the next 20 years, NASA will launch the Terrestrial Planet Finder. This collection of highly sensitive space telescopes will actually recognize if a planet has the right atmospheric gases, such as water vapor, carbon dioxide, methane, and ozone, all necessary to sustain Earth-like life.
With that picture, we can then take the light from that planet, spread it out into all of its colors or wavelengths, blue, green, yellow, red, even into the infrared, and analyze that light for the chemical composition, maybe even the biological composition of that planet. What we might find are signs of life in a variety of forms. For example, oxygen.
When it comes to producing larger Earth-like life, a planet or moon needs oxygen. 3.4 billion years ago, the only life on our planet were single-celled microbial organisms. But as this primitive life absorbed energy from the sun, it formed a green pigment called chlorophyll. This produced photosynthesis, a chemical process which converts carbon dioxide and water into energy, with oxygen as a waste product. Single-celled organisms evolved into cyanobacteria, one of the Earth's earliest structures. Cyanobacteria injected vast amounts of oxygen into the oceans and air. New life emerged, which diversified and developed into large multicellular species, and eventually, man.
Our Earth would not have oxygen in the atmosphere if it were not for plant life. By photosynthesis, generating the oxygen that otherwise would oxidize rocks and vanish. So Oxygen is a biomarker for the Earth. If we could examine another Earth-like planet and detect oxygen in its atmosphere, it would be one key sign, not yet definitive, but one element of the argument that that planet too has photosynthetic life.
At NASA's Ames Research Center, astrochemist Lee Biebout and her colleagues are cultivating oxygen-bearing ecosystems in a greenhouse. They're microbial mats, complex microbe communities often found on muddy and sandy sediment surfaces, in hyper-salty waters and carbonate beaches. These microbial mats are the oldest known living ecosystems on Earth. Biebout wants to know if these microbes could exist on other planets, producing oxygen, thereby enabling life to evolve.
We know that with the advent of oxygen production through photosynthesis, these microbial ecosystems, in particular the cyanobacteria, began to change our atmosphere. We're very curious how that happened, how that transitioned, how these microbes adapted and spread to diversify and fill so many niches on our planet. This is important in helping us decide what to look for on other places, say Mars or other extraterrestrial places.
If life exists far off in our galaxy, or in distant galaxies, will it truly be Earth-like? On our planet, all life contains DNA, a long chain of molecules that holds the blueprint for every living thing. It allows life to duplicate and branch out, essentially creating the tree of life. But are there alternatives?
Maybe life on another world is still carbon and water-based, but doesn't use DNA at all. Maybe it uses a completely different type of molecule to store information. That would be very exciting.
And could there be life that doesn't require DNA, carbon, or water?
Well, it may be that ours is kind of a crappy planet compared to what's out there, that there may be other planets that are much more optimized for advanced life.
Many of my colleagues, which are doing astrobiological research, they're looking for life that unkindly I might typify as stupid life. And they're looking for microbes mostly. There may be something a little bit bigger.
Some astrobiologists want a close encounter with something more than just a microbe. They're looking for intelligent life that's perhaps even smarter than us. The search for life extends beyond looking for slimy bacteria. In astrobiology, a crack team of scientists wants to make contact with something much grander.
SETI, of course, is looking for intelligent life in space, but it doesn't just stop there. They have to be not only intelligent, but they have to be technologically competent.
The Search for Extraterrestrial Intelligence Institute, better known as SETI, uses radio technology to listen for radio leaks from alien civilizations. It's based on the premise that humans need to communicate, so perhaps alien nations also want to get their message out.
What we try and do is simply try and eavesdrop on signals, either radio waves that we could pick up with our antennas, or flashing laser lights. They might be using big lasers to aim pulses of light in our direction. I am not man, I am microbe. I'm also Seth Shostak for the SETI Institute, whose mission is to understand the nature and origin of life in the universe.
And I'm Molly Bentley. Welcome to Are We Alone?
Who remind you that there's more to life than just what you find at your local zoo.
At SETI, senior astronomer Seth Shostak hosts a regular radio show that's podcasted,
where we're bugging out with microbes.
There are so many cohabitating with you. You're listening to Hand Me Microbe.
Showstack broadcasts lively, yet informative science-related news to Earthlings, as well as other advanced civilizations that have the means to listen in.
Cynthia Phillips, thanks for joining me today. We are so fond of radio for listening that we started a weekly radio show in which we, in a sense, broadcast. A lot of people are interested in SETI because everybody's interested in aliens in the same way that just about everybody's interested in dinosaurs. People are just interested in that. So we're trying to take advantage of the fact that they're interested in what we do to get them interested in some broader subjects in science and also technology.
SETI has been listening for signals since the 1960s, but ET hasn't phoned in. This silence has fueled skepticism.
Now we're going to find lots of planets with life. I'm guessing that intelligence will be rare, but they won't be smart in the way that humans are smart. That's going to be rare. But again, that's just my intuition.
Aliens can't get here at faster than the speed of light. Physics doesn't allow that. And that means, since we've only been broadcasting for, say, 60 years, they can't be coming from a planet more than 30 light years away. Well, the number of stars within 30 light years is pretty small.
Our universe is over 12 billion years old. Planet Earth has only been around for over 4.6 billion years. Therefore, there are planets millions and billions of years older than us. So if there's life beyond the Milky Way galaxy, it potentially could be millions to billions of years more advanced than us.
I think that the truly intelligent species out there, if they ever happened upon us, would maybe regard us as we regard ants or bacteria, as some primitive example of life. Anybody we meet is going to be much more advanced than us, at least certainly much more aged than us in terms of how long they've been a civilization.
If intelligent civilizations do exist beyond Earth, what would they look like?
But if we find intelligence in space, it's moved on beyond biological intelligence and moved on to machine intelligence. A thinking machine that represents 1 million years of evolution beyond where we are, who knows how it's built? All you know is that it might be really, really smart.
There's no logical reason why there shouldn't be machines from other worlds exploring our planet, coming into our airspace, maybe even attempting to interact with us in some way.
Whether we find a trace of bacteria or a high-tech civilization, any discovery of life will revolutionize the way we think about the universe and ourselves. Until then, it remains one of the greatest unsolved mysteries of all time.
So we're going to see a real zoo out there when we finally do discover alien life. All sorts of different ways of coding information and making molecules, causing the phenomenon of life.
The people that work on this field are geeks, so we imagine making contact with alien geeks, right? And we're going to have fun talking about equations together, but maybe we'll end up making contact with alien hipsters or bohemians, and we'll need some other form.
So, life as we don't know it.
Thanks for choosing Ancient Revelation, your #1 Ancient Investigations channel. We are sorry, all of our operators are busy at the moment. Please subscribe and we will get back to you as soon as possible. Thank you.